Okay, last talk is in presence again. It's on herd design, and it's given by Ronen.
Okay, so good morning. This is joint work with Itai and Rann from the Technion. So in an ideal world, markets aggregate information, but we know that in reality this doesn't always happen, and there's some nice theoretical reasons for why it doesn't happen. One that I really like is this idea of social learning, which is a situation where agents learn from observing others, and we know that in such situations they often do not aggregate information. And these kinds of models have been used to model various kinds of phenomena where information aggregation fails. Things like herding and fads and acid bubbles and things like that. So in the classic social learning model, you have a sequence of rational agents. Each of these agents observes a signal, a private signal from some exogenous information source, plus they observe the behavior of previous agents, and then take some best action. And we know that when this happens, they may end up not aggregating information, but instead herding on some inferior action. Now, our observation, or a simple observation, is that the action that they end up herding on depends on this exogenous information structure. And so a natural question is, where does this information structure come from? So where does it come from? So we study the question through the lens of Bayesian persuasion, which, as you all probably know, is a question of how an information designer called the sender can use information revelation to cause some agent to behave in a way that the information designer wants. And we suppose that this sender is the one who designs the information structure in the social learning model. Okay, and we basically ask, can the sender in the social learning model manipulate the crowd as well as she can manipulate any individual? Okay, so that's the question that we ask. Our main result is a necessary and sufficient condition under which the answer is yes. Okay, which I'll show you some intuition for today. Our proof for the sufficiency is constructive. It's kind of interesting that the optimal structure here is very different from kind of the standard optimal structures that you get in traditional Bayesian persuasion.
Sorry, Ronnie. Sorry to interrupt you. But actually, the screen sharing is off on the virtual space, so maybe the technical staff can handle this. Sorry about that.
Okay, you see it now?
Yes.
Okay. I didn't show anything too important on the slides yet. Okay, but now my clicker's not working. Okay, so there's some related literature. In the interest of time, I'll just show you that it exists. And the rest of the talk, I'm just going to go through an example. So here's the example. So suppose we have a seller, and the seller wants to sell identical copies of some product. And let's suppose that with probability 1/5, this product is high quality, and otherwise it's low quality. And we have these consumers who are interested in the product when it's high quality. They get positive utility. So they don't have to know for sure whether it's high or low quality. Let's just suppose that they're willing to take the chance and buy the product as long as they believe that it's high quality with probability at least 1/4. Okay, and the seller wants just to sell as many copies of the product, gets a utility of 1 whenever he makes a sale. Okay, so here's a picture that we'll see a few times in this talk. On the x-axis, I have the buyer's belief. Goes all the way to 1, but I've cut it off. Mu is the prior. That's his initial belief, 1/5. And on the y-axis, we're going to plot the seller's profit. Okay, so this is the indirect utility function, Bayesian persuasion. As long as the buyer's belief is less than this threshold of 1/4, the buyer will not buy, and so the seller's profit is 0. As soon as the belief is above 1/4, the buyer is willing to buy, and the seller's profit goes up to 1. Okay. So first, let's talk a little bit about Bayesian persuasion. So in Bayesian persuasion, as you know, the seller is going to commit to some information structure. Okay, a randomized function g from the state to some message. This is the signal. The state is either the high or low quality, whether the good is high or low quality. That's realized. The buyer is going to get the signal, the function from the state to the message, and take an action. So a simple example, the seller could commit to a truthful revealing signal, g of theta equal to theta. In this case, what's going to happen? Well, with probability 1/5, the state is high. The buyer gets the corresponding message, makes a purchase, and otherwise it's low, and he doesn't make a purchase. The seller's utility is 1/5. Okay, can she do better? Well, yes, this is the standard Bayesian persuasion stuff. You look at the concavification of this indirect utility function. You look at the prior belief, where it intersects the concavification, and then you look on the y-axis, that's the optimal seller's profit, which in this case is about 4/5. Okay? The optimal information structure here, on the high state, always revealed that it's a high state. On the low state, you randomize between a low and a high signal. And the randomization is such that on getting the high signal, the belief is exactly 1/4. Right? Make the buyer exactly indifferent between buying and not, and let's just suppose that in that case, the buyer does make the purchase. Okay, so the expected profit is 4/5, and what I want you to notice is that if you look at the buyer's posterior belief, it's either 0 or 1/4. Right? If you got the low message, he believes that good is high quality with probability 0. If you got the high message, it's 1/5. Okay, so we're going to say that the optimal value is supported on these two values. Right, these are the two endpoints of the line segment of the concavification where the optimal value appears. Okay, this is standard Bayesian persuasion stuff. Okay, so now let's talk a little bit about herding. So herding is a little bit different. Here we have an exogenously fixed information structure. Okay, we'll give it the same name, G. And let's look at a simple example. Let's suppose it's a symmetric information structure, meaning that when the state is high, the message is high with probability p and low with probability 1 minus p. And when the state is low, the message is revealed low with probability p and high with probability 1 minus p. Okay, so it's informative, but it's not perfect, and it's symmetric on the two sides. Okay, p here is greater than 1/2. Each buyer in the herding model is going to observe the decision of the previous buyers, whether they bought or not, and going to update his belief based on the pattern of purchases that he saw. That's the public belief. Plus, he's also going to get a conditionally independent signal from this information structure, and then he's going to make a decision based on these two things. Okay, so let's run through a simple example. Okay, we're still in this buyer-seller example. And here's our first buyer. Our first buyer shows up to the market. His initial belief, his prior belief, is 1/5. And now he's either going to get a high or a low signal. Now, if he gets a high signal, that's going to shift his belief upwards. Okay, and let's suppose that it's above 1/4, and so he makes a purchase. On the other hand, if you got the low signal, that's going to shift his belief downwards. It's below 1/4, it's below 1/5, and so he's not going to buy. Okay, that's our first buyer. So let's suppose that he got the high signal, he made a purchase. And now let's suppose the second buyer shows up. Now the second buyer observes what the first buyer did. Right? He saw that the first buyer made a purchase, so he can infer that he must have had the high signal. So he can infer the first buyer's signal, and so he adjusts his prior belief to be equal to the posterior of the first buyer. Okay, now he's also going to get a high or low signal that's going to shift his belief upwards or downwards. If he gets the high signal, he's still above 1/4, so he buys. He gets a low signal, now he's below 1/4, so he doesn't buy. Either way, the third buyer can now infer what both first two buyers got. Okay, so that's a less interesting case. So here's the more interesting case. Let's go back to our first buyer, and suppose that he got the low signal. He didn't buy. Now the second buyer shows up. Second buyer either gets a high or low signal, but notice that either way, his belief is still below 1/4. Right? So in either case, he's not going to make a purchase, regardless of his signal. Right? His action is independent of his signal, which means that the third buyer doesn't get any new information from the second buyer's action. Right? He can just infer what the first buyer got plus his own information. And basically what happens here is all learning stops. What happens with the third buyer now, right? The second buyer always doesn't buy. The third buyer also always doesn't buy. And now we've got a herd on not buying the product. Okay, this is a herd. Okay, so what we saw here is that if the first buyer doesn't buy, we're going to end up with a herd on no buying. A symmetric argument shows that if the first two buyers buy, then we've got a herd on buying. Okay, and here's one thing to notice. In the first case, the first buyer didn't buy. Sorry, one more case. If we get alternating, then we're back to the prior. And at some point, we're going to end up on a herd, either on buy or no buy. OK. Now, at this point, when there's a herd, the public belief is going to be either the belief of starting at 1/5 and not buying, and it's going to stay there, or it's going to be on 2 buy, right? What happens when 2 people get the high signal, and it's going to stay there, right? Because there's no more learning, so the public belief stays fixed at one of these 2 posterior beliefs. Okay, it's supported on these 2 respective beliefs. Now we can calculate the probability of getting a herd on buying. Okay, it's a straightforward calculation. And just for now, just notice it's going to depend on P, the probability of getting the accurate signal in this information structure. Right? Remember, it was a symmetric signal with P and 1 minus P. And what P is going to determine the probability of a herd on buying or not buying. OK, so I've told you a little bit about Bayesian persuasion. I've told you a little bit about herding. So now let's look at our paper, which is basically a happy marriage of the 2. So we're going to suppose that the seller faces buyers who observe their predecessors, like in the herding model. But the buyer can also design the information structure to which the seller can design the information structure to which these buyers have access, like in Bayesian persuasion. OK, now we know that buyers eventually are going to herd on one of the 2 actions, buying or not buying. And of course, the seller wants to maximize the probability of a herd on buying. And the question is, to what extent can she do this? What information structure should the seller choose to maximize this probability? So let's try some simple ideas. So one is to not reveal any information. This is not great. Buyers don't learn anything. They remain at 1/5 and never buy. Profit is 0. You could try full revelation, in which case they learn the state, and profit is 1/5, right, in the long run. That's the probability of the state being high. You could try the optimal Bayesian persuasion signal, right, that we saw before. And this does lead to the optimal profit from the first buyer of 4/5, right? That's this thing. However, notice that if a buyer doesn't buy, then now everybody learns that the state is low, right? And if the state really is low, then at some point, some buyer is going to get the low signal and not buy. And from that point on, nobody else is going to buy, because everybody's learned the state. So actually, this is no better than the fully revealing signal. So can she do better? Well, we could try this P1 minus P kind of signal. Okay, and we said the probability of a herd on buy depends on P, so we could optimize this P. And this yields this expected value, which is bigger than 1/5, so that's good. But it's much lower than 4/5. Okay, our question is, can the seller do better? And in particular, can she get 4/5? And our answer for this example is yes, but we're going to need a much richer information structure. Okay, in particular, any information structure is going to lead to a herd. Sometimes it's going to converge. What that means is it's going to converge to 2 posterior beliefs. And what we'd like is that these posterior beliefs that the herd converges on are 0 and 1/4, right? The beliefs that support the optimal value in Bayesian persuasion, right? The 0 and 1/4 on here. We're going to construct something that's almost optimal. For any epsilon, it's going to be epsilon and 1/4 plus epsilon. And we're going to need a lot of signals. And just some terminology, we're going to say that a high signal is one that sways the belief upwards, and a low signal is one that sways the belief downwards. And this is what it's going to look like. There's going to be a bunch of high signals, a bunch of low signals. And if we want to converge to 0 or 1/4, our signal is going to have to satisfy 3 things. The first thing it has to satisfy is that if we're somewhere above epsilon in the public belief, we want to be able to get to 1/4. Otherwise, we're stuck. Okay, on the other hand, if we're below epsilon, then we want to stay there. Then we don't want to run away too far. And this gives us an upper bound on the strength of the positive signals. The second thing we want to satisfy is that if the belief is already above 1/4 plus epsilon, then we want to stay there. We don't want to shift back down. And this gives us a lower bound on the accuracy of the low signals. The last thing is if the public belief is somewhere in between, then we want to jump upwards, maybe, but we never want to jump too far. We want to stay close to a quarter. Okay? Sorry. And basically, we showed that this is possible to get all these. And then we get a herd where the beliefs converge to something close to 0 and something close to 1/4. Can the seller always guarantee the optimal value? The answer is no. Here's an example where he can't. Here there are two products, V1 and V2. I'll just show you the picture due to time. Basically, the profits are a little bit different for the two versions, and also the buyer wants different versions for different beliefs about the quality. The nice thing about this example is the optimal value is still 4/5, it's the concavification, but here it's actually impossible to get this value. And the intuitive reason is, if you think about starting at 1/5, we want to be able to get to 1/4. So there has to be a signal that's strong enough to get us from 1/5 to 1/4. But in that case, it would also get us from 1/4 past 3/10. So we can never converge to something close to 1/4. Okay, so I've shown you two examples, one where it's possible to get the optimal value, one when it's not possible. Our result is necessary and sufficient conditions characterizing when it's possible and when it isn't. I'll show you a picture of what that looks like. So think about these two intervals, LK and LM. These are the intervals of beliefs where the beliefs that support the optimal value are on. So 0 and 1/4 lie on this interval IK and IM. In a more complicated example, maybe this is what the indirect utility looks like. Here also, we have some IK and IM. Okay, so what we're going to do is we're going to convert each one of these intervals to log likelihood scale. So now it's not from 0 to 1, it's from -infinity to infinity. And basically, the optimal value can be attained if the lengths of these intervals in log likelihood scale are the following. The second interval is the largest, the first interval is the second largest, and all the intervals in between are smaller still. Okay? If that holds, then we can get the optimal value. If it doesn't hold, we cannot. Okay, so I'm out of time, so just a quick recap. We look at a herding model where the designer designs the information structure. We ask, can the sender manipulate the crowd as well as she can manipulate any individual? I showed you some necessary and sufficient conditions under which the answer is yes, and hopefully I've convinced you that the signaling structure is more interesting than the standard Bayesian persuasion structure. Yeah, that's it.
Thank you. Questions?
Thanks so much for the great talk. So I'm just wondering, there is a kind of an alternative information design problem in which you can design how much of the previous actions you want to reveal to the next buyer. I was just wondering if you have any comments on that problem.
So actually, that was in the slide with the related literature that I skipped. So people have looked at design questions in herding models where the question is, how can we maybe improve communication or have the communication in a particular form to get rid of the herding problem, to get better information aggregation. So there's some work on that. From the point of view of a designer who has some other interests, I'm not sure. Yeah.
So again, nice work. Is there a geometric characterization of what is possible, like concavification, but for the herding?
What is possible when the optimal is not possible?
Yeah.
So we don't have a characterization. For a while we thought we did, but then we found some counterexamples. We thought that our result here was also a characterization, but it turns out it's not, so we don't know.
Can you briefly explain where the log likelihood transformation comes from?
Where it comes from. Yeah, so kind of the intuition that I gave for why it's not possible is the belief starts at somewhere, and we want to be able to get to some other interval. But we don't want to overshoot. Now, we don't want to be able to go from here now to the next interval. Now, to measure how we go from one interval to the next, right? It's just computing using Bayes' rule to compute the posterior. And so if you want kind of the distance from here to here, and from here, right? If I start at a prior here, and I get some signal and jump here, I get the same signal, I jump here, it's not the same distance. right? It's the same distance in log likelihood scale. So then kind of the distances in signal accuracies are comparable, no matter where you start.
I just have a clarification question. So your signaling scheme is it a dynamic one that at every time step you're going to have a signaling scheme that depends on the history, the realization?
Yeah, so that's a good question. So no, it's one signaling scheme, and we commit to that same signaling scheme throughout. But it's a conditionally independent draw from that same signaling scheme. If you could have a dynamic one, then the problem is trivial, because then you would commit to the Bayesian persuasion optimal for the first guy and just never reveal any more information.
What about computational stuff? Do you think about like anything? Is there a computational dimension to this problem, like complexity, approximation?
Well, I know that verifying whether you can get the optimal value is straightforward here, because it's just comparing lengths of intervals. I don't know.
You have only mentioned how to decide whether we can get such a scheme, but just how to just get that scheme. Is there a general algorithm to compute this?
To find the optimal structure when it exists? Or in
yes.
general? So in general, I don't know. When you can get the Bayesian persuasion optimal, then our sufficiency proof is a construction that achieves this. I mean, it's not unique, but...
But if it's not as good as the Bayesian persuasion, can we still get the best that we can get?
Well, then I don't know what the best is. I don't have a characterization of what is the best that we can get. So I don't know. Yeah.
Final question.
So if I'm Sarah, could I just persuade one by one? I observe the action, and then for the next person, I just use Bayesian persuasion.
You're asking about this. So you observe everybody before you,
Right.
and you draw a signal from you draw a message from the signaling structure.
No. So I'm Sarah. I observe
Yeah.
the action.
Mm-hmm.
For the next person, I just use Bayesian persuasion. So this is a different model. So I'm considering sort of a...
So you're thinking of a model where you have a new structure for each agent after observing the actions.
Right. That's right.
Yeah, so that's the dynamic model. That was also Haifang's question. So here, we're fixing the same signal throughout. Because otherwise, you would do the Bayesian persuasion optimal signal for the first guy, and then never reveal any more information, and that would give you the optimal. And you can't do any better than that.
Yes. I'm saying, is this the right sort of the practical way of persuading?
So maybe I didn't understand the question. I'm sorry.
No.
In the interest of time, let's take the discussion offline, and let's thank Ronen again and everyone in the session.